So here is another example, very similar to the previous one, the graph we've got here. Here, what is added, I mean, in terms of information compared to the previous graph. So let's see again. You have your function that you want to optimize, and you've got your constraints here that is expressed in the plane x, y, and I've tried to figure the image of your constraints value here. All right. What wasn't in the previous one? Here we've got some level lines, okay? And here we see that the bluer the color, the lower the value. So if we want to minimize, we want to know the point where, if I look at my constraints, it's going probably to be somewhere around here. Where it's going to go to the lower values of my function. If I follow my curve of constraints, the red curve of my constraints, I want to find the point on this red curve that will give you the lower value if you take the image and look at the image for function f. Okay, so maybe we can have a look at that first GeoGebra animation, which I find quite good. So let's open that. So here it is. Here you've got something similar. You've got your surface, this red surface. You've got at the bottom on that right panel, you've got the level lines of your function, and you have on the left panel, you've got something corresponding to, you've got the XY plane that shows you the level lines, the red level lines of your function, and the blue lines is figuring the constraints that you want to consider. So that's the admissible set. It's going to be the points that belong to that red that blue circle. Okay, this is why we see that yellow dot following that blue circle on the left, and on the right the values that the function takes for specifically for the points of this circle. Okay, so that if you again graphically want to get the minimum or maximum, you visually see that there's going to be something like 2 points that correspond to minimum value and 2 points that correspond to maximum value. The arrows that you see moving with the points on the left panel are representing two things. The gradient of your function, so which is orthogonal to the corresponding level line. If you remember that from the reminders on Terra expansions, we get that the gradient is always orthogonal to a level line. That's one thing. And the other arrows, so it's a bit of a pity that we don't have two different colors, but the other arrow, the one that is constantly orthogonal to the circle, is the gradient of your constraint, because it's just orthogonal to your blue circle. Okay, all right. And if you spot the points where you're going to get the minimum and maximum values, which are actually located at the axis, if you look at the left panel, you see that it goes to the brighter values on the y-axis, and it goes to the darker values when your circle, your constraint circles meets the x-axis. All right, and you see that at those points you've got something interesting going on. You get that the two arrows, the two gradients, are going to be aligned, well, collinear. Okay, and actually this is not a surprise. This is really the basis of all the reasoning on constraint optimization. Let's get back on that slide. So here on the drawing that we've got here, I wanted to do something very similar. We've got the constraints curve, that is this red curve that you've got here, and we've got the dotted blue lines that are corresponding to the level line of your function. And as you see that what's happening is that, well, two things. When your constraints, if you follow the points of your constraints, so you're on your constraint curve, and you follow the points, and you are looking for, let's say, I don't know here, that would be the smallest value you want to minimize your function. What you're looking for. The main idea is that actually at this lowest points, which should be located here graphically here, you're going to have that your constraint is tangent to the level line of your target. It can't be otherwise, okay? It can't be otherwise for the following very simple reason. Let's say that you've got something like this. So I should have taken another color. Let's say that these are the level lines of your function, and this is the lowest value, okay? And this lowest value being here, and the high values are here. Let's say you want to minimize, and that your constraint is some curve looking like this. So what's happening? If it's crossing one level line, it means that on one side, the value you've got here is going to be higher than the value you've got here for your function. So for your constraints, the value corresponding to points of your constraints here are going to be higher than the values you've got here. Every time you're crossing a level line, it means that on one side of this level line, you're going to have higher or lower values. But what's happening when you get tangent to a level line, so like what I'm trying to do here, it means that the points, so you're still following your constraints, you're traveling on your constraints here, and you approach here, you get high value, you touch this is lower value than what you had before, and then traveling again here, you get a higher value than the one you've just reached. So this is it. At the minimum, or at the maximum, we're looking at the maximum, we have that the constraint is constraint curve, in that example, is tangent to a level line. Okay? So that's actually the basis of all the reasoning on constraint optimization, all right? At your optimum value, your constant curve is going to be tangent to the level line. And another way to say that is to say that, as you know, that the gradient of your function is orthogonal to the level line, and the gradient of your constant is orthogonal to your curve, then you get that the two gradients have to be collinear. Okay, so the gradient of the function is orthogonal to the level line. At the optimum, the constraint is tangent to the level line, so the two gradients have to be collinear. Okay, and actually this is going to be the main result that we're going to get, the order one result.